Hello everyone, I am Dr. Krishna Sarker. Here in this session, I will be going to discuss about controllable canonical form or first companion form. Lecture series on state space analysis, lecture 22. This is state space analysis, control system subjects. So our new topics, controllable canonical form or first companion form. So what is controllable canonical form? Why controllable canonical form? Advantage of controllable canonical form. So our first overview. What is the overview? State space representation of transfer function. State space representation of transfer function. State space representation in controllable canonical form. Transfer function to state space, state matrix, state diagram, signal flow graph, and stability of the system. Application of the controllable canonical form. This is our overview. So first, what is companion form or controllable canonical form or first companion form? This technique is convenient in the case when the planned transfer function is given in a non-factorized polynomial form. So this is the very important term, non-factorized form. When non-factorized form, we can apply companion or first companion form. A linear time invariant system is described by the transfer function of the form. This is the linear time invariant system transfer function. Ys by us equals to overall transfer function, where ys equals to output of the system and us equals to u of s equals to input of the system, and equals to beta 0 s to the power n plus beta 1 s to the power n minus 1 plus beta 2 s to the power n minus 2 plus beta n minus 2 s square plus beta n minus 1 s to the power 1 plus beta n, and denominator terms s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 plus this is alpha n minus 2 s square plus alpha n minus 1 s to the power 1 plus alpha n. Beta 0, beta 1, beta 2 beta n are coefficients, s coefficients, and alpha 1, alpha 2, alpha 3 also coefficients of the systems. So this is the overall transfer function, and our targets transfer function too. This is the transfer function. What is the target? This is our transfer function. Our target transfer function to state equation calculation, then state matrix calculation, then state equation to state diagram, and state diagram to signal flow graph and system stability of the system. This is our target. So next, for this system, an auxiliary variable is introduced such that the transfer function is split as, this is the split form, ys by u of s equals to zs by u of s, ys by zs. So left hand side what? Left hand side equals to output by input, ys by u of s, and right hand side zs by us into ys by zs. If zs cancel, if zs cancel, suppose this is zs, this zs cancel, then ys by u of s. So zs by us and ys by zs, what is the block diagram? This is our block diagram representation for zs by us and ys by zs. Here u of s equals to system input or reference input. This input may be step, ramp, parabolic, impulse, any type of input you can apply. And this is the first block, and the transfer function zs by us, because zs equals to output of the system and U of S equals to input of the system. Ratio out ZS by US is called transfer function. And for second block, input signal equals to Z of S, and the overall output equals to Y of S, and YS by Z of S equals to second transfer function. So this is the transfer function for general systems. And YS by US equals to beta 0 S to the power n to beta n divided by S to the power n alpha 1 S to the power n minus 1 dot 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 alpha n. Split first factor 1 by S to the power n, 1 by denominator terms, 1 by denominator terms. What is the denominator terms? 1 by S to the power n plus alpha 1 S to the power n minus 1 plus alpha 2 S to the power n minus 2 plus dot 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 alpha n minus 1 S to the power 1 plus alpha to alpha n, or S to the power 0. This is S to the power 0, but S to the power 0 equals to 1. That's why only alpha n, and into beta 0 S to the power n plus beta 1 S to the power n minus 1 plus dot 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 beta n minus 1 S to the power 1 plus beta n. So 1 by denominator, this is the first block, and this terms second block. So this is the block diagram representation. Overall, US equals to input and 1 by S to the power n to alpha n. This is the first block, and output by input, first transfer function ZS by U of S, and second transfer function YS by ZS. This is the cascade form or series form. Then ZS by US equals to, already discussed, ZS by US equals to 1 by S to the power n plus alpha 1 S to the power n minus 1 plus alpha 2 S to the power n minus 1 plus dot 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 alpha n minus 1 S to the power 1 plus alpha n. This is the first transfer function, ZS by US. This is ZS and this is the US. So next term, YS by ZS. Next term, YS by ZS. This is the second term. This is the second term. This is the second terms, and this is the first term. So YS by ZS equals to what? YS by ZS equals to beta 0 S to the power n plus beta 1 S to the power n minus 1 plus beta 2 S to the power n minus 2 plus dot 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 beta n minus 2 S square plus beta n minus 1 S to the power 1 S to the power 0 beta n. Then our development starts with a transfer function of the form ZS by US. First operate ZS by US. This is the case number 1. So which can be written as cross multiplication. First our cross multiplication ZS into denominator. S to the power n plus alpha 1 S to the power n minus 1 plus alpha 2 S to the power n minus 2 plus dot 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 alpha n whole into Z of S equals to U of S, equals to U of S. So first cross multiplication and then multiply with ZS. So S to the power n, first term S to the power n into ZS plus second term alpha 1 S to the power n minus 1 into ZS plus alpha 2 S to the power n minus 2 ZS plus dot 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 alpha n minus 2 S square ZS alpha n minus 1 S to the power 1 ZS plus alpha n Z of S equals to U of S. So after multiplication, the corresponding differential equation is, this is the differential equation, nth order differential equation by using inverse Laplace transform. By using inverse Laplace transform, first term S to the power n Z of S. So after inverse Laplace transform, this is nth order differential equation dn zt by dtn. Second term alpha 1, this is alpha 1 and S to the power n minus 1. So dn minus 1 zt d to the power n minus 1 dot 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 dot. Last term an into zs. So a alpha n into zs, alpha n into zt, and this is the alpha n minus 1 S to the power 1 zs. So alpha n minus 1 this terms equals to, this is equivalent to s to the power 1 into zs equals to dzt by dt, dzt by dt. This is the first order differential equation. And this is the nth order differential equation where output equals to z of t, where output equals to z of t, and this output variable because this is the position. This output position z of t equals to position of the system, and if rate of change of z of t, then this is the dzt by dt equals to velocity, and if again rate of change of zt, then d2zt by dt2, this is called acceleration. That means position differentiate, this is velocity, velocity differentiate, then this is acceleration. If acceleration integrate, this is velocity, and velocity integrate, this is z of t. So this is the variable output. So put z of t equals to state variable, another state variable dzt by dt2, another state variable d2zt by dt2, dot dot dot, up to nth order differential equation. And u of t equals to system input or reference input. Then having developed a realization of the simple transfer function, we are now in a position to consider the more general form to get one state variable model of the system with a state variable starting at the right hand proceeding to the left. The corresponding differential equations using this identification of the state variable are. So this is our nth order differential equation, and state variables are first state variable z of t position. So position equals to x1, this is the first state variable. Differentiate both sides, then we get z dot t equals to dzt by dt equals to, again right hand side differentiation, x1 dot equals to another state variable x of x2, and again differentiate both sides, then this is equals to z double dot t, and this is equals to d2zt by dt2 equals to x1 double dot equals to x2 dot equals to another state variable x3, and again differentiate with z of triple dot t equals to d3zt by dt3 equals to x1 triple dot equals to x2 double dot. This is x2 dot, that's why x2 double dot, x3 dot, another state variable x4, then dot 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 zt n minus 1 dot equals to dn minus 1 zt by dt n minus 1 equals to xn minus 1 dot equals to xn. This is another state variable, this is another state variable. And finally, for nth order differential equation, zt n dot equals to dn zt by dtn equals to x1 dot x1 n dot equals to dot 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 xn minus 1 double dot equals to xn dot. This is the nth order differential equation. So this is the very important terms. Zt equals to what? Zt equals to x1. This is the state variable, and x1 dot equals to x2, and third term x2 dot equals to x3. This is the x3, and x3 dot equals to x4, and similarly dot 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 xn minus 1 double dot equals to xn dot. These are state equations, x1 dot, x2 dot, x3 dot, and xn dot equals to what? This is the xn dot. This is the xn dot. So put zt equals to x1, dzt by dt equals to x2, and d2zt by dt2 equals to what? d2zt by dt2 equals to x2 dot equals to x3. Similarly, this is equivalent to xn dot. This is equivalent to xn dot. This is equivalent to xn dot. So next, put state variable or state equation, determine the state equation. So xn dot equals to minus alpha 1 xn minus alpha 2 xn minus 1 minus dot 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 minus alpha n minus 1 x2 minus alpha n x1 plus u of t. This is the state equation because left hand side differentiation terms and right hand side free of differentiation terms. This is the innate state variable equation. Xn dot equals to state variable equation. So what is the state equation? X1 dot. What is the x1 dot? Already proved x1 dot equals to x2. X1 dot equals to x2 and others coefficient 0. That's why 0 into x1 plus 1 into x2, 0 into x3 plus 0 into x4 plus 0 into x5 dot 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 0 into xn plus 0 into u of t. Again x2 dot equals to what? X2 dot equals to already proved x3. So put x2 dot equals to x3 and others coefficient 0. So 0 into x1 plus 0 into x2 plus 0 into x4 plus 0 into x5 dot 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 0 into xn plus 0 into u of t. Similarly, x3 dot equals to x4. X3 dot equal to only x4 and others coefficient 0 into x1, 0 into x2, 0 into x3, 0 into x5, 0 into xn minus 1, 0 into xn, 0 into u of t and dot 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 xn dot equals to minus alpha n x1 minus alpha n minus 1 x2 minus alpha n minus 2 x3 minus dot 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 minus alpha 2 xn minus 1 minus alpha 1 xn plus u of t. These are all state equation x1 dot x2 dot x3 dot 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 xn dot. The state equations already discussed. These are all state equation. Then what is the state matrix? This is x1 dot x1 dot. What is the x1 dot? X1 dot equals to only x2. So others coefficient 0. X1 dot equals to only 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, only x2. And ut also 0. And x2 dot equals to only x3 and others coefficients are zeros. And x3 dot equals to only x4 and others coefficient 0. And what is the xn dot? Xn dot coefficient minus alpha n. This is the 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 minus alpha n. Minus alpha n minus 1, minus alpha n minus 2, minus alpha 2. This is the minus alpha 2. This is minus alpha 1 and x1, x2, x3, x4 dot 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 xn and this is the coefficient 1. So ut coefficient only 1. So this is the state matrix. This is the state matrix. Then what is the z of t? What is the z of t? Z of t equals to only x1. Already proved state variable z of t equals to x1 and x3, x4, x2, x3, x4 dot 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 xn are 0. So output z of t equals to only x1. That's why z of t equals to, this is the matrix, state matrix, z of t, output matrix, mainly output z of t. The state equations are already discussed. This is the state equation. Then this is the state diagram, which very, very important. For state diagram, ut equals to reference input. This is the ut terms. This is the ut. So put first u of t, u of t. This is the u of t. This is the u of t. So put u of t first and then xn dot. What is the xn dot? Xn dot equals to minus alpha 1 alpha n x1 minus alpha n minus 1 x of t minus alpha n minus 2 x of 3 dot 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 u of t. So this is the u of t. This is the x1 xn dot. This is the xn dot. This is the xn dot. So put xn dot equals to this equation. Proved. Xn dot equals to xn dot equals to, this is the equation, state equation. So put xn dot and xn dot integrate xn minus 1 dot and xn minus 1 dot equals to xn. Xn minus 1 dot integrate xn minus 2 dot. At xn minus 2 dot equals to xn minus 1. xn minus 1 2 dot integrate, and similarly dot 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 x3 dot integration x2 dot equals to x3, x2 dot integrate x1 dot equals to x2 already proved. At x1 dot integrate, this is the x1, and x1 equals to z of t. This is the z, this is z of t, not z1 t. This is z of t, state variable. So already discuss. And what is the x1 coefficient? X1 coefficient alpha 1. This is the x1 coefficient. This is the x1 coefficient alpha 1. So put here x1 coefficient alpha 1. So x1 into alpha minus alpha n. This is the x1 into minus alpha n, and this is the minus alpha n. This is the addition. And second term, what is the second term? Second terms, alpha minus alpha n minus 1, x2, x1 dot coefficient equals to x2, x2 into minus alpha n minus 1. This is the second terms. This is the second one. This is also again added, and xn dot equals to already these two proofs. And third terms, alpha n minus 2, this is the alpha n minus 2 into x3, and again addition. Then xn minus xn dot equals to this plus this plus this. That means this plus this plus this. And this is minus alpha 3 into xn minus 2. This is xn minus 1 into minus alpha 2. This is alpha 2 minus alpha 2 into xn minus 1. And this is also added. And minus alpha 1 into xn. This is the minus alpha 1 into xn. So this is the ladder diagram, or this is the state diagram for this states equation. This is the state diagram. Controllable canonical form or fast companion form state diagram. The state matrix, this is the state matrix, x1 dot x2 dot x3 dot 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 x n dot equals to this matrix, and this is the x1 x2 x3 x4 dot 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 xn 0 0 0 0 dot dot dot. This is dot 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 1 equals to u of t. This is equivalent to state equation x dot equals to x plus bu. This is equivalent to x dot equals to ax plus bu, where x dot equals to this. This is the state equation, because left hand side derivative terms and right hand side free of derivative terms. So x dot equals to x1 dot x2 dot x3 dot x4 dot 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 xn dot, and a equals to this matrix, x equals to this matrix, and b equals to this matrix, and u of t, u equals to u of t, u equals to u of t. And this is the special type of matrix. Because why special type? Because only this diagonal matrix, super diagonal matrix 1, and last row coefficients of the systems. This type of matrix is called companion matrix or controllable canonical form of the systems. And if the matrix of this matrix is n, then system will be controllable. And that means if rank equals to n, then system controllable, otherwise uncontrollable. Otherwise uncontrollable. Then what is the output system? Z of t equals to only x1. Only x1, other terms 0. So y equals to cx plus du. In this position, du equals to 0, and c equals to 1 0 0 0 0 0 0, and x1 to xn. This is the zt equals to output, not final output matrix. The output is given, already proved. That means this is the zs by us already complete. Then second case, ys by zs, ys by z of s equals to what? Ys by z of s equals to beta 0 s to the power n plus beta 1 s to the power n minus 1 plus beta 2 s to the power n minus 2 plus dot 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 beta n minus 2 s square plus beta n minus 1 s to the power 1 plus beta n. this is the second term, this equation for this block. So ys by zs, this is the ys, this is the ys, and this is the zs. So this is also transfer function, output by input, output by output equals to ys, and zs equals to system input. This is the zs system input. So what is the output? So calculate output. Just cost multiplication, zs into this equation, zs into this. Y of s equals to what? Y of s equals to beta 0 s to the power n into z of s, beta 1 s to the power n minus 1 whole into z of s, beta 2 s to the power n minus 2 into z of s, beta n minus 2 into s square into z of s, beta n minus 1 z to the power 1 equals to z into z s, and beta n z of s. So multiply, just multiply by z of s. Then taking inverse Laplace transform, and we get ys equivalent to, again, ys equivalent to y of t, y of s equivalent to y of t, beta 0 s, beta 0 constant, and this is the s to the power n z of s, s to the power n z of s equals to what? S to the power n z of s equals to s to the power n, s to the power n. This is the nth order differential equation, and all initial conditions are 0. That's why d to the power n zt by dtn. And next term beta 1, this is the beta 1, and s to the power nth order, s to the power n minus 1 order differential equation. So differentiate, and we get beta 1 z to the d to the power n minus 1 zt by dn t to the power n minus 1 plus beta 2 z d to the power n minus 2 zt by d t n minus 2 dot beta n minus 2. This is beta n minus 2. S square means second order differential equation. That means d2 zt by dt2 plus b1 beta 1 d to the power n minus 1 zt by dt to the power n minus 1, and finally beta n z of t. In this position, z of t equals to out. This is the z of t position, and dzt by dt equals to velocity, and d2 zt by dt2 equals to acceleration. So this zt variable, this is the variable. So put z of t equals to, already proved, z of t equals to x1, z of 2 equals to, this is equivalent to actual x1, this is equals to x1, z of t equals to what? Z of t equals to that state variable x1, and dz2 by dt equals to, this is equivalent to x of x2, this is equals to x2, this is equals to x of 2. Then realization of the transfer function is now straightforward. The output, this is the xn dot, this is dn d to the power n zt by dtn equals to xn dot, this is equivalent to xn dot. So right here xn dot, this is equivalent to xn dot, and this is equals to xn, this is equals to xn minus 1, this is equals to x1, this is equals to x2, already proved, and this is equals to x3 state variable. So put, and finally output y of t equals to beta 0 x to the power x dot n plus beta 1 xn plus beta 1 xn plus beta 2 xn minus 1 plus beta n minus 2 x3 plus beta n minus 1 x2 plus plus beta n x1. This is our final output y of t, final output y of t. So the state equation, these are states equation already discussed, and this is the output y of t equals to beta 0 x to the power n plus beta 1 xn plus beta 2 xn minus 1 plus beta n x1. So what is the state diagram? What is the final state diagram? Lower portion already discussed, because this is the beta, this is the xn dot minus alpha 1 x1, this is the minus alpha 1 into x1, this is the minus alpha 1 into x1, xn dot equals to, and this is minus alpha n minus 1 into x2, this is minus n minus alpha, or minus alpha n minus 2 into x3, this is minus alpha 3 into x4, xn minus 2, and minus alpha 2, xn minus 1, minus alpha n, alpha 1 into xn. So add it, and xn dot equals to, this is the equation. And what is the output y of t equals to beta 0 xn dot? This is the xn dot, so beta 0 coefficient multiply xn dot into beta 0, y of t equals to. So what is the output? Y of t equals to beta 0 into, this is the beta 0 into beta 0 into beta 0 into xn dot plus beta 1 into xn. This is beta 1, this is xn. So beta 1 into xn, this part beta 1 into xn. Again beta 2 into xn minus 1, this is the beta 1, beta 2 into xn minus 1, and beta 3 into xn minus 2. Similarly dot 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 beta n minus 2 into x3 plus beta n minus 1 into x2 plus beta n into xn. So output y of t equals to beta 0 xn dot plus xn into beta 1 plus xn minus 1 into beta 2 plus dot 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 x3 into beta n minus 2 plus beta n minus 1 into x2 plus beta n x1. This is the final output and overall state diagram. This is the overall state diagram, but in this diagram, this is the xn dot differentiation term. This is the disadvantage. So put here xn dot. What is the xn dot? Xn dot equals to minus alpha n x1 minus alpha n minus 1 x2 minus alpha n minus 2 x3 dot 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 u of t. So put here xn dot and calculate final y of t, and right hand side free of differentiation terms, our target. Then the state diagram already discussed. This is the actual state diagram. Controllable canonical from, as consequence, y of t already discussed. Y of t equals to beta 0 x to the power n plus beta 1 xn plus beta 2 xn minus 1. So put xn dot. What is the xn dot? Xn dot equals to minus alpha n x1 minus alpha n minus 1 x2 minus alpha n minus 2 x3 plus dot 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 u of t. So put here xn dot equals to this term. That means put here this term. Sorry, this is the xn dot. Put here this value. Xn dot equals to minus alpha n x1 minus alpha n minus 1 x2 x, then put beta 0 into minus alpha n x1 minus alpha n minus 1 x2 minus alpha n minus 2 x3 minus alpha n minus 3 x4 dot 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 minus alpha 1 xn plus u of t, and others value beta 1 xn, beta 2 xn minus 1 plus dot 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 beta n minus 2 x3, beta n minus 1, this is beta n minus 1 x2 plus beta n x1. Then multiply by beta 0 and common x1, x2, x3. This is the common term. Beta n minus alpha n beta 0. This is the beta n minus 1 minute. This is the beta n x1, beta n x1, and this is another coefficient x1 minus alpha n into beta 0, alpha n into beta 0. So x1 common, beta n, this is the beta n minus alpha n beta 0, minus alpha n beta 0. Similarly x2 common of x2, then beta n minus 1 minus alpha n minus 1 beta 0. Similarly x3 common beta n minus 2 minus alpha n minus 2 beta 0. Similarly dot 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 x3 common beta n minus 2 minus alpha n minus 2 beta 0, x4 common beta n minus 3 minus alpha n minus 3 beta 0, and xn minus 2 common beta 3 minus alpha 3 beta 0, xn minus 1 common beta 2 minus alpha n minus alpha 2 beta 0, and xn common. This is the xn term. This is the xn term. This is the xn term. Xn term and xn beta 1 minus alpha 1 beta 0 minus alpha. This is the xn term and this is the xn term. So beta 1, this is the beta 1. 1 minute. This is beta xn coefficient. So common xn. This is the xn beta 1 and this is the another xn coefficients. This coefficient minus alpha 1 beta 0 and finally beta 0 into u of t. This is the beta 0 into u of t. This is the beta 0 into u of t. So this is the beta 0 into u of t. So this is the final output for companion, first companion form or controllable canonical form. Then using this output, what is the state diagram? So beta 0, this is the beta 0 into u of t, beta 0 into u of t, this is the beta 0 into y of t equals to beta 0 into u of t plus x1 coefficient, first xn coefficient. What is the xn coefficient? This is the xn coefficient, beta 1 minus alpha 1 beta 0. This is the beta 1 minus alpha 1 beta 0 into xn, this part. And this is the beta 0 into u of t. And this is the xn minus 1 into beta 2 minus alpha 2 beta 0. This is the xn minus 2. This is the xn minus 1. This is the x minus 2 beta 2 minus alpha 2. This part. Beta 2 minus alpha 2 beta 0. Beta 2 minus alpha 2 beta 0. And this is the beta n minus 2 minus alpha n minus 2 beta 0. Alpha n minus 2 beta 0. And then finally beta n minus alpha n beta 0 into xn, x1 into x1. This is the x1 function. So x1 multiply by beta n minus alpha n beta 0. This is the first terms. X1 into this. So multiply x1 into this term. Then this is the final overall block diagram of the systems. Overall block diagram already discussed. The states and output and equation is shown below, organized in vector matrix form, are given below. X dot t equals to what? Xt plus b of ut, yt equals to cxt plus dut, and this is the A matrix, and b equals to 0 0 0 dot 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 1, and this is the C matrix, beta n minus alpha n beta 0, beta n minus 1 minus alpha n minus 1 beta 0, and dot 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 beta 1 minus alpha 1 beta 0, and d equals to beta 0. D equals to beta 0. So what is the signal flow graph for controllable canonical form or fast companion form? What is the signal flow graph? This is the signal flow graph for fast companion form. This is the beta, this is the forward path u of s, this is the u of s or u of t, and output yt or y of s. So this is the forward path. This is the forward path. Then this is the beta 0 feedback. Sorry, beta 0 forward another path. This is the beta 0 forward another path up to yt. And next forward path beta 1 beta 0, beta 1 minus beta 0 into alpha 1, beta 1 minus alpha 1 beta 0, and this is beta 2 minus beta 0 alpha 2, this is beta 2 minus beta 0, beta 2 minus alpha 2 beta 0, and this is the beta n minus 1 actually this path, this is the beta 1 minus, this is the feedback path, next feedback path, this is the another feedback path, and this is the beta n minus 1 dot 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 beta n minus 1, and this is the beta n minus alpha n beta 0. This is the beta n minus alpha n beta 0, beta n minus alpha n beta 0. And lower portion, this is the minus alpha n, this is minus alpha n. So this is minus alpha n, this is minus alpha n minus 1. So this is minus alpha n minus 1, this is minus alpha n minus 2, this is also minus alpha n minus 2 dot dot dot, this is minus alpha 2, this is minus alpha 2, and this is minus alpha 1, this is minus alpha 1, and this is the integration 1 by s, this is all one integration, this is another integration, this is another dot 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 integration. So this is the signal flow graph for this state diagram. Only signal flow graph. This is the only signal flow graph already discussed. And another form of the system, this is beta 0 path. So this is the beta 0 path, this is the beta 0 path. And this is the beta 1, this is the beta 1 also, beta 1, this is beta 2 forward path, this is beta 2 dot dot dot, this is beta n minus 1, this is beta n minus 1 up to yt, and this is the beta n, and this is the beta n into x1. And reverse, this is minus alpha n, this is minus alpha n, this is minus alpha n minus 1, this is minus alpha 2, this is minus alpha 1. So this is the another block diagram and signal flow graph. That means this is the state diagram and signal flow graph for controllable canonical form. This is the overall signal flow graph already discussed. If the direct path through beta 0 is absent, that means if beta 0 absent, then the scalar D is 0 and the row matrix C contains only the beta I coefficients. So when beta 0 0, then D equals to 0. When beta 0 absent, that means beta 0 absent, D equals to 0. This is single input, single output systems. The matrix capital A has a very special structure. The coefficients of the denominator of the transfer function proceeded by minus sign from the string along the bottom row of the matrix. Already discussed, bottom row only coefficients of the systems, bottom row negative coefficients of the system. The rest of the matrix is 0 except the super diagonal terms, which are all unity. In matrix theory, a companion form. In matrix theory, a matrix with this structure is said to be in companion form. For this reason, we identify the realization as companion form, realization of the transfer function. We call this is the first companion form or controllable canonical form. So, what is the conclusion? The matrix, from matrix, the last column, the last row, only negative coefficients. Minus alpha n minus 1 minus alpha n minus 2 dot 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 up to minus alpha n, and super diagonal element only 1, others terms 0. This type of matrix is called canonical forms. So application of the controllable canonical form on application of the first companion form. The controllable canonical form is very useful to determine the controllability of the system. This is the very important sentence. The controllable canonical form is very useful to determine the controllability of the system. So system controllable or uncontrollable, this is identified from this matrix. The controllable canonical form is very useful to determine the stability of the system. And the controllable canonical form is very useful to determine the state equation, state matrix, state diagram, signal flow graph, and stability of the systems. This is our main target actually: state equation, state diagram, signal flow graph, controllability, stability of the system. For what condition the system will be stable? For what condition? When rank of the, what condition system is controllable? When rank of the system is n, then system will be controllable. If rank equals to not equals to n, then system uncontrollable. This system uncontrollable. So thank you.